Okay, so we'll sort of finish up with what we were doing with the hydrogen atom. So remember that we have this radial equation, which makes up the radial. Okay, it's useful for constructing the psi r theta phi, or the wave function for the hydrogen atom. We found out that whenever the angular momentum is conserved, okay, we have this YLM theta and phi part, and we are now interested in finding the radial part. And the radial part we found out depends only on n and L. Okay, so this psi has these indices n, L, m. Okay, n is something that we found out that must be discretized to get a proper solution. In fact, what was it? Let me just write that from my notes. So what we had was that instead of this r of r, okay, if I use u of r over r, then this u of r turns out to be something which can be expressed as, well, let me describe it in terms of my unitless quantities. So these things I have to make a table also because I need them. Okay, so there is this variable k, which is equal to square root of minus 2m e over h bar squared. And this rho variable, the dimensionless variable, is just k times r. And in terms of rho, I had, remember, rho to the L plus 1 times e to the minus rho. These are the asymptotic parts. And then I had a some sort of polynomial expansion. So let me just start with the 1. It's going to be normalized anyway. Plus, let's call it C1 rho plus C2 rho squared plus dot 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 all the way to C capital N rho to the N. Okay, so there's a cutoff. Remember, if you don't put that cutoff in, then this series goes to e to the, it becomes proportional to e to the plus 2 rho, which is something I don't want, so I truncate it at a certain point. Okay, obviously this n can be 0, in which case then I will just get 1. And to have this normalized, okay, I also need a constant in general. So this is the general form of u of rho that we found. And there is this recursion relation which gives us these numbers. Okay, so Cj plus 1 was equal to a ratio, let me just check that, to L plus 1 plus j minus rho 0. Okay, j plus 1, j plus 2, L plus 1. Okay, so this is something that we found last time, Cj. Okay, and let me write down what rho 0 is so that I have all my references correct. It's equal to m e to the 4 divided by 2 pi epsilon 0 h bar squared times k, that's k. Okay, so that's that, and what we said was that, okay, now in order to cut this off, okay, so that this is 0 at some point, I need to have 2L plus 1 plus this largest power in the series, n, okay, must be equal to rho 0, okay? And rho 0 is that stuff there. Okay, so let's just repeat that part of the algebra. This is m e to the 4 divided by 2 pi epsilon 0 h bar squared k. Okay, so we notice that everything depends really on what this integer is. Okay, L plus 1 plus n. The energy will depend on that. Okay, so let me try to find out what this is. So this k, remember, is just square root of minus 2m minus 2me h bar squared. So if I square both sides, I get 4n squared equals m squared e to the 4. This rho 0 is e to the 4. That's surprising. It's e squared. Sorry about that. Okay, so that's e squared. So now it becomes e to the 4. And I get 4 pi epsilon 0 h bar squared and a minus 2m e over h bar squared. So this is, I am having trouble squaring expressions today. Okay, and I have something like that. Okay, so some stuff will cancel, but basically I'm going to get E is equal to minus, because of that minus sign, m squared e to the 4, and then 32 pi squared epsilon 0 squared h bar squared and an n squared. And last time I told you that this, if you calculate what this gives you 13.6 electron volts. It has 12 units of energy, right? Divided by n squared. Okay, so that's where we were last time. All right, so that means I have a structure for the wave functions which looks like that. So the energy, you see, depends only on this number n, okay, which we call the energy quantum number, and that the value of n limits what L and n can be, right? So I have this n equal to L plus 1 plus n. So this is the order of the polynomial. So it can be a zero order polynomial, 1, 2, 3, etc. L, the angular momentum index, can also be 0, 1, 2, 3, etc. N, small n, can be 1, 2, 3, etc. Okay? Yes?
How do you have m squared in the energy? Because
yeah, okay, so it should go that way.
also the m is the mass, right?
M is mass, right. Is there any other m? Oh, okay, it's not the m of the magnetic quantum number. It's the m that comes in from the energy. Okay, so m is the mass. Okay, so we don't have the magnetic quantum number at this stage except in the wave function over here. Okay, so in this expression, m is the magnetic quantum number. At all other places, it's mass. Okay, so now going back to what this then all depends on, this u obviously depends on the maximum cutoff over here, power of rho, and also L. Okay, but customarily we don't write it in terms of the capital N, but we write it in terms of L. So this u we write as small n and L. Okay, so it will be a function of n and L. If n and L are given, then of course capital N is known, right? Okay, in fact, let's try to, well, before I go any further, let's also look at what K is. So K is going to be equal to, you see it has a square root of energy. So I have to multiply this by minus 2m and try to obtain a square root. Okay, so please check my algebra. So m here becomes m squared, so its square root is m. Then I have e squared divided by, so multiply by 2, this becomes 16, so it becomes now square root is 4 pi epsilon 0 h bar n. Okay, and k has to have units of 1 over distance, so that kr is unitless. So this is equal to 1 over some distance a times n. And distance a is approximately 0.5 angstrom, okay, and is known as the Bohr radius, because this also comes out from the calculations of Bohr. Okay, so k times rho, which comes k times r, which is rho, then is just r over a times 1 over n. Okay? All right, so let's just look at the first few functions. By the way, these things have names. Okay, this polynomial is a polynomial which which was analyzed earlier by mathematicians, and it's one of the Laguerre polynomials. But okay, it's not really. It doesn't help very much in physics to know its name. In any case, let's look at the form of these wave functions. Okay, so I have this n, which describes the energy, and then I also have various possibilities for L, and that then implies I'm going to get a certain n, right? And for all of these things, we have this, let's call it RNL, which is UNL of R divided by R. So it's going to have some form, some normalization constant, instead of rho. Okay, let me in fact continue writing in terms of rho. Okay, so it's going to be, well, maybe I shouldn't. Okay, so it's going to be rho to the L, which means R to the NA to the power L, right? Then e to the minus R over NA, that's the e to the minus KR part. And then I have the polynomial, 1 plus, okay, C1, R over NA, okay, plus C2 R to the R over NA squared, and so on, until I get to Cn R over NA to the nth. Okay, so that's the form of the solution. Let's just look at a few of these things. Okay, one thing that I want you to notice is that if you look at this recursion relation from Cj to Cj plus 1, you see I put in larger and larger values of j until at some point this cancels that, right? So that means this term is really smaller than that one. Okay, so I keep getting negative numbers consecutively until it reaches 0. So all of these constants, so a better way of writing this would probably be something like minus rho 0 minus 2L plus 1 plus j, okay, divided by the denominator. Okay, so I'm going to get a negative number here, okay, negative number here until I hit the correct value of rho 0. Yes?
Hocam, when we were writing the u r over r in r instead of rho,
Yeah.
Did we take the 1 over n times a in the capital A? There is something like that.
What did we take into A? Which A?
Rho, that capital A.
Okay, that's normalization, yeah.
We take it inside it. So.
Yeah, okay, I mean, you can put it here if you like. Okay, that's going to be C0, but then you still need a normalization constant. It's not guaranteed that it's going to be normalized. Okay, because we are solving a differential equation, a linear differential equation. Okay, this will satisfy the equation, but in general it will not be normalized. If you multiply this function by 5, it will still satisfy it because it's a linear differential equation. But physically, we need a normalized one. So, okay, I'm just pulling that out. Okay, so it will be an alternating series with pluses and minuses. So let's start with n equal to 1. Okay, so n equal to 1 is the smallest value that we can have. And then that means L, okay, I already have a 1 there. So L n can only be zeros. Okay, so this polynomial, in fact, now is very simple. A, because L is 0, and this is to the 0th power. So I have just something like e to the minus r over a. Okay, so that's the simplest case, okay, corresponding to n equal to 1. What about n equal to 2? Now I have a choice because I can have L equal to 0 and n equal to 1, or L equal to 1 and n equal to 0. Okay, so let's go one by one. So I have either that or 1 and 0. Okay, so let's see what this gives us. This is going to give me, again, a normalization constant, something to first power in, okay, polynomial, but r to the L is 0. Okay, so I am going to get just 1 plus minus, okay, some number. In fact, let me give you those numbers. Okay, in fact, okay, so let me do it like this. R minus, so I need my glasses. 1 minus r over 2a, so this is our rho to the first power, and then multiplied by e to the minus r over 2a. You see this is an exponential, but it extends farther away, okay? It extends twice the distance as n equal to 1, okay? That's why, because higher, as you go to higher energies, the electron is farther and farther away from the nucleus, okay? So in some sense, that's the effect of the centrifugal term. Okay, so this L equal to 1 is going to give me A. Now I have an rho to the L term here, so it's going to be R over 2A to the first power, and then a 0th order polynomial, which is just that, and e to the minus r over 2a. Okay? So that's what that looks like. So let's go ahead. Let's see. Then let's just do one more. Okay, 3. Then L can be 0 and n can be 2. L can be 1 and n can be 1, or L equal to 2 and 0. Okay, so those are the now new possibilities. So let's see what this is. This is going to be A, okay, L to the 0, so no prefactor there with R, and it's something with second order minus, let me see what it is. So this is 302, okay, twice R over 3A, and plus, you see I have to go up to n equal to 2 over 3 R over 3A squared. And the exponential now is going to be e to the minus R over 3A. Okay, so it extends even further. So 1 is going to be A, 1 power of R to the R over 3A, and then a polynomial which will go to first order, which will be 1 minus 1/2 R over 3A. Exponential is the same, e to the minus R over 3A. Okay, 2, is easiest because it's going to be R over 3A squared, and 0th order polynomial, so nothing there, e to the minus 3R over 3A. Okay, so you get the idea. That's how these things go. And you just generate more and more terms as you go to higher order n. Okay, just to give an idea about how these things are behaving, you see, if we try to plot these things, of course, they are, it's good to compare terms which look alike. Okay, so let me just plot here something like R, and it's going to have an n and an n minus 1. Okay, so it's going to, I'm just going to look at things like 1, 0, 2, 1, 3, 2, etc. Okay, so, and I'll plot them as a function of R over A, which is nice and unitless. Okay, so over here I can have 1, 2, 3, and so on. Okay, so the simplest case, R10, is going to start someplace. Okay, so this is my R10, and say simple exponential, right? Yes?
Can you remind what was big N standing for?
Big N is the order of the polynomial. Okay, so here you see this goes up to 1. Here it goes to 0 because it doesn't even appear. Here it goes up to second order. Okay, so that's our n. Okay, and here it's 1 again. So n, capital N, is the power of R, largest power of R in the polynomial. Okay, so I have this exponential. Okay, it's easy to draw exponentials, but if I want to compare, I have to be careful. So the exponential has this nice property that if I construct a tangent to it, it hits, okay, the value of its decay length on the x-axis. So it's something which does something like that. Okay, so that's how it behaves. Okay, so similarly, if I look at R21, that's also an exponential, but has an R multiplying it. Okay, so it will extend more or less. Okay, it will start from somewhere lower because it will extend longer. So when I normalize it, I'll get a smaller coefficient. So it will, okay, more or less try to do something like this. But it starts proportional to R, so it will do something like this. Okay, whatever. Okay, so this is R20. And then if I look at R30, you see that's going to start quadratically and then extend, okay, even longer. So this is going to be R30. Yes.
So should we consider these?
I'm sorry, I'm not labeling these correctly. This is R21, this is R232, right? Yes.
Should we consider these wave functions? For example, this is the wave function for single electron hydrogen system, right?
Yes.
So when we don't measure, should we consider the electrons wave function as infinite mixture of all these?
Yes, in general, okay, so the pure states, the energy eigenstates, are things which look like R and L of R and Y, L, M of theta and phi. Okay, so this is something, okay, so I can represent this as N, L, M. Okay, so it's a state for which I have an N, L, M, and they are all going to be orthogonal to one another. Okay, so the LM orthogonality is orthogonality of the YLMs, but these things R's for the same N and L will again be orthogonal to one another. Okay, so maybe a good exercise, just take two N and M's, say L equal to 1, and take this function, okay, with L equal to 0, and take this one L equal to 0, and see their orthogonality. Okay, let's see. Am I saying something correct? Yes.
Capital N is 3, will both C1 and C2 negative and C3 positive?
Yeah, okay, so if you look at the fourth order stuff here, okay, which so if I look at n equal to 4 and L equal to 0, that means the capital N is going to be 3, right? So in that case, I'm going to get something which looks like 1, okay, minus this rho over R over 4A, some coefficient in front, plus R over 4A squared with some coefficient in front, okay, minus some coefficient R over 4A cubed. Okay, so that's what the polynomial will look like if n is equal to 3, if capital N is equal.
One negative and one positive.
Yes, it always alternates. Okay, it alternates because if you look at this recursion relation, you see I have to get the consecutive term from this equation, and j starts from 0, then becomes 1, then becomes 2, then becomes 3, okay, until it hits the proper value here so that you get a 0 in the numerator. So that means this term is smaller than rho 0, okay, so that means this numerator here is positive, or the coefficient is negative, or if you look at this, the numerator is negative. Okay, so the signs alternate. If Cj is positive, I get a negative Cj plus 1. Okay, so it's an alternating sort of thing. Yes?
How are we calculating the coefficients of these? I'm sorry.
How are we?
Yes.
From the recursion relation.
Yes, but what are we using j instead of j? And what are we using instead of j?
What are we? Okay, so let's do one of them. This is actually fun, but okay, maybe I'll assign it as homework so you'll have even more fun. Okay, so let's, for example, see how I would calculate it. Let's take a nice long one. How would we calculate this object? So L is 2, I'm sorry, L is 0, so n, I'm looking at this line, right? So n is 3, L is 0 and capital N is 2, right? So those are, I want to generate the polynomial for that. Okay, so now I go to my nice equation over here and start applying it. So I'll just choose as C0, okay, as 1. I can choose any number I like, but they are all proportional to one another. Okay, I'll have to normalize it at the end anyway. Okay, so I'll just take that. So now, what is C? Okay, so let's go all the way from the end. I know that I'm going to get a C1. Okay, so I'll get a minus C1 rho plus C2 rho squared, and that's it, right? And then C3 is going to be 0. And if C3 is 0, then everything else is 0. Okay, so the series is going to cut off there. Now, if that's going to be the case, so if C3 is going to be 0, that means if I look at this equation, okay, that says that C2 is going to be equal to, okay, minus rho 0, okay, minus 2L plus 1 plus J, and J is 2, right? So that's the maximum value. Okay? So, and I know that L is 0.
Shouldn't J be 1? Yes.
J should be 1. C2 is Cj plus 1, so J must be 1.
Yeah, but I'm sorry, I'm looking for C3. Sorry about that. C3, so this is going to be my capital N, right? That's where I cut off. Okay, and I want to get a 0. The reason for that is I want to find what rho 0 is, okay? Okay, so I have something in the denominator. So what does that tell me? Rho 0 for this case is going to be 2 plus 3, 6. Is that correct? L is 0, 1 plus 2. Okay, so rho 0 is 6. Okay, so that's apparently if it cuts off at C2 and I get a C3 equal to 0, rho 0 must be 6. Okay, so now I go back. I'll try to find what C1 is. So C1 is going to be equal to, okay, I quote that equation. C1 is going to be 2, okay, I'll write the full thing first and then we'll discuss JL plus 1 plus J minus rho 0, which was 6, right? And in the denominator, I have J, am I doing this correctly? Okay, I'm writing the upper equation, but that's okay. J plus 1, okay, J plus 2L plus 1. Okay, now I need help with my algebra. So this is C0, which is 1. So this is going to be 2. L was 0, so 1. And J at this point is 0. Okay, so I get 3, right? L is 0. 3.
This is 5 minus 4. 2 minus 6 equals minus 4.
Okay, so it's minus 4 divided by, J is 0, so it's 1. And then 0, 0, just 2. Is that correct? So it's
don't
equal
have
to,
2 in front of -4. We only have -4.
oh, okay, I'm sorry. And then this is just equal to -2. Okay, so I have found this -2. Okay, so we check that. Now if I want to find what C2 is, so now I'm after this number here. I have to do this again. Okay, so it's going to be equal to 2, L is 0 plus 1, but J is now what? J is 1 minus 6 divided by, okay, J is 1, so it's 2 times J is 1, so it's 1 plus 2, right? So it's going to be equal to 2, 4 minus 2 divided by 4. So I get minus a half
Times 3.
times 3. Why?
1 plus 2.
Hmm?
We got 2 times 3. Because we have 1 plus 2 in the denominator.
Oh, okay. No, but this is wrong, right? This is 2 times 3. Is that okay? This is so 1 over 3. Why do I have a 2 over 3 there?
You
Check.
should multiply it by C1.
Hmm?
You should multiply it by C1.
Oh yes, I have to multiply it by C1, right? Which is minus 2, okay? So minus 2, which gives me plus 2 over 3, okay? So now I have this one also. So that's the idea, okay? So you start with, you have to make sure that you have the proper row 0 so it cuts off someplace. Okay, so row 0 must have a certain value so that it cuts off at a certain value. So the first thing that you have to do when you are looking at any one of these things is to make sure that you get the proper value of row 0, because now if I try to calculate C3, okay, that's something I did in the first step, I know that I'm going to get 0. Okay, so it will cut off at the third point. Yes?
You have said that you have found the result for the Bohr radius in the laboratory with the Schrödinger equation, and you have said that Bohr found it purely accidentally. So I found it a bit weird because we are arriving with the same result.
Okay, but
so I think there should be some valid starting point there too. So can you show what are the common points?
well, there are not really that many common points, because if you look at Bohr equation, what Bohr does is Bohr assumes that the electron is going around the proton and therefore has certain standard angular momenta. Okay, and for the ground state, it says, okay, it's going in the lowest orbit and the angular momentum is equal to h bar, which is not correct. N equal to 0, ground state has 0 angular momentum. So how can you rescue a theory like that? Okay.
Then how it turns out to give.
You see, when it's something interesting. When we sometimes grade freshman exams, okay, so you see that a student writes down in the first few seconds of the exam all of the equations that he knows about physics on an exam paper, and then just puts in from the question, okay, this is asking for a force, so where's the force equation there? So what do I need? A mass, etc. And they put all of these things together, and at the end, they get an answer which is, okay, dimensionally correct, because he's using an equation, putting mass, okay, length, etc., everything correctly, then you get obviously something with units of force, okay? And then the answer is perhaps off by a factor of 2 or a factor of pi, and then he argues, when he doesn't get any points, that, look, I made some mistake of 2 over 3, and you are just taking off points because just my answer is not correct. Okay, so Bohr got the answer right, but if I'm grading his exam paper, he wouldn't get very much of a grade from that problem. Okay, so that's obviously Bohr is a great guy. I don't once the Schrödinger equation developed, he had one of the largest contributions to quantum mechanics. But his initial idea, although intuitively very nice and all, quantitatively it's okay, what we call fortuitous, okay, so lucky in some sense. Okay, he probably tried lots of other things which didn't work. So, okay, any other questions? How are we doing on time? Let me try to show you what the other functions look like. Well, these other functions, if you look at them, you see this is something which goes down like this. Okay, this function will oscillate like this. Okay, so this one will do something like this. It will start linearly and then decay. So you can just sort of go through all of these things. This is, again, something which will oscillate, but will have two nodes, okay, because of these alternating sort of thing. This will start again as a function of r, but will go to 0 after one oscillation. This one, okay, will go to, okay, so it will start quadratically and will decay, something like that. Okay, so those are the main features of these things. Obviously, these things result in certain types of symmetries, etc., in the problem, but it's best to study those things as we get to applications. Okay, so when we get to the applications of this thing, we'll go into more detail. Okay, so how do we use this stuff?
For that, can I ask you a question?
Yes.
Are these Legendre polynomials?
No, these are Laguerre polynomials.
Oh, all right.
Okay. And there are no Legendre polynomials, they are Legendre polynomials. Okay. Okay. I'm sure my pronunciation is also not acceptable to a Frenchman. All right, so now we have these energy levels. The lowest one is n equal to 1, okay, and it has to be L equal to 0, okay, so let me just put this as 1, 0, 0, okay, so this first index is the energy index, energy quantum index. This is the total angular momentum index, and this is the magnetic quantum mechanic index, okay, the angular momentum Z component, which usually couples to the magnetic field. That's why we call it the magnetic index. Okay, so this is the n equal to 1 case, and it's minus 13.6 electron volts. Then I have the n equal to 2 case. Okay, so that has possibilities. So it's n equal to 2. I can have 0, 0. But I can also have n equal to 2, L equal to 1. And then I have a large variety of things here. Okay, so I can have L 1, 1. Okay, 2, 1, 0. 2, 1, minus 1, and 2, okay, 2, 0, 0 is already there. Okay, so these are the L equal to 0 state, and I also have 3 L equal to 1 states. So all of these things have the same energy. Okay, so that's going to have an energy because it's n equal to 2 minus 13.6 electron volts over 4. Okay. Then the next order thing, okay, is going to be, okay, even smaller gap, minus 13.6 electron volts divided by 9. This is n equal to 3 case. And you see these things accumulate closer and closer to the, okay, to the top. All right, so the n equal to infinity limit obviously is the zero energy limit. So you have all these things accumulating there. Okay, so now what you can do is obviously the electrons want to stay in the lower energy levels. So this is a big gap. Okay, so even this gap is quite a bit. So 3/4 of that is something like 9 electron volt difference, right, between these things. 9 electron volts is an extremely large amount of energy for everyday life type of things. Okay, so KT, room temperature, corresponds to something like 40 milli-electron volts. So things like the surface temperature of the sun is something like excuse me, something like few electron volts, 2 electron volts or something. So most hydrogen at room temperature is, if it's a single atom, it will be in its ground state. Now, you can excite this to higher energies. Okay, you can, if you're a gas or these things, you can pass an electric arc through them. So what happens is that the electron may jump to some other energy level over here. So it starts from, let's call it some initial energy level, and falls into a final energy level. Okay, so in fact you can hit the atom so hard that this electron just flies away. So you could you're just left with a proton, but then it may capture an electron from a free electron from the outside. Okay, so you have many possibilities. So what is the energy difference here when you do something like this? Well, delta E is going to be equal to the initial energy difference, let's call it EI, minus EF. Okay, so the initial energy is going to be, okay, they are all going to be proportional to minus 13.6 electron volts. And then the initial energy is 1 over Ni squared, and the final is 1 over Nf squared. Okay, so just to rearrange terms, 1 over Nf squared is going to be the larger number. 1 minus 1 over Ni squared is going to be the initial smaller number, okay, 13.6 electron volts. So what do these things look like? So obviously you are going to get, when this happens, you are going to get a photon out with frequency h bar omega. So omega is going to be proportional to the energy. So if you now look at the, okay, spectrum, so if you carry out spectrography of the light that's coming out of hydrogen, what do you find? You find if N final is equal to the ground state, that's going to be the largest energy gaps, which will be the larger energy differences. Okay, so you are going to get a bunch of lines here which correspond to various transitions. Okay, they'll start with perhaps, okay, let me try to be more accurate. Okay, so they are going to accumulate, okay, to larger and larger values. So this is going to be, okay, minus 13.6 electron volts, well, plus now, the energy difference, times, okay, the bigger one, 1 minus 1 over N initial squared. So it's just going to accumulate over here on h bar omega equals 13.6 electron volts. So those are transitions from the from any one of these things to all of these states. Not all transitions are equally likely. We'll see that later on in the course, but that's what you have. Now, you can also have transitions into this second n equal to 2 state. So those are going to be 13.6 electron volts. And now I'm going to have 1 over 4 because n is equal to 2 in the final state minus 1 over ni squared. So depending on what ni squared is, now I'm going to get a series of lines here, again accumulating more towards the right because there are more higher energy initial states. Okay, so I get a whole bunch of states like that. Okay, so that's the structure of the spectrum that you get. So these things have names, okay, Rydberg and Lyman, whatever. And these are important tools for studying the spectrum of gases that you have. Obviously, if you have a different gas, there will be different energy levels. And you can just, by looking at the spectrum, you can see the type of gas you have in hot objects like stars and such. So that is an important tool to analyze content of gases at high temperatures. Okay, let's have our break and then we'll move on.